Is it visible?
Yes, sir.
Okay, so quickly I'm going through the theory that we discussed last class, and in this class mainly we'll be focusing on the implementation of threads and a bit of thread programming. Okay, so what we found is threads in operating system. It helps us in creating uh, executable units or scheduling units is having less overhead compared to creating a new process. And the idea of creating threads, or the feature of threads, that started in 90s, early 90s, and the standardization came in the mid 90s, or and in fact it requires some kind of like there should be some sufficient hardware in terms of number of processors. So in true sense, the availability of multiple CPUs or processors that were available in a cost effective fashion, maybe from mid 2000, that is 2004-5. So in true sense, the multi-threaded applications that actually came or that were become popular in the 2000 onwards. Okay, and we'll be mainly focusing on POSIX thread API. POSIX stands for a portable operating system interface, which if you write your thread applications using POSIX APIs, then it will be you can execute it in all standard operating systems which supports POSIX standards. And we found that there are different possible say operating systems or uh, computing systems which have different kind of, so when we talk about thread, it can be associated in different forms. And this fourth one, this is the one that is the most flexible and generic, and where you can so these are operating systems which supports creation of multiple processes, and each process can have in turn multiple threads defined within it or created within it. So that's a most generic uh, way of considering thread implementation. And what we found, there are different multi-threaded applications, and these are the three possible options when it comes to the implementation of or realization of the threads. One is the user level threads, where the existence of the threads is only visible in the user level, and the kernel is completely unaware of the existence, which if you use will not be able to exploit the presence of the processors. This KLT, the kernel level thread, where as the name suggests, the kernel is aware of the presence of multiple threads, and obviously each from the user's end also, user space also. So the kernel is aware of the threads, and as a result, the scheduling, the basic scheduling unit is indeed a thread. However, here the basic schedulable unit is a process yet, because the kernel is not aware of the threads. And this is the last one, which is a combined one, where if a kernel has created 2 or 3 threads, now you can have uh, a different kind of mapping in the user space, where the 3 threads in the kernel level can be mapped into 2 threads in the user level, and so on. So it is completely flexible. So let us come to the implementation of threads or thread program. So before we come to the implementation, so first thing is, as we found that if you have got a single processor, just a single CPU, so it is intuitive to know that if you, even if your application has, or application process has created multiple threads, and because you have got one CPU, so you cannot exploit the presence of threads, right? So that is not possible. Okay, so have you heard about hyper threading? Any idea what hyper threading is? how many processors? Hello, can you hear me?
Yes, sir.
So how many
Yes, sir.
processors do you have in your machine? I mean, anybody. So it might differ, but how many processors you have? Have you ever checked?
Yes, sir. It can be found in the task manager.
Yes, sir.
So this is as it shows. So in the Windows, if you check, you will find it here in the performance. If you see, so these days we are aware of dual core, quad core, like that, right? So dual core means you see there are two cores. So what does this refer to? Two cores means there are two physical CPUs. Physical means you can think of the two separate units, independent units. So two CPUs are there in the motherboard, and these are logical processors. What does it mean? Can you see this? This is a snapshot from my machine. I have got two cores, but I have got four logical processors. So what is the difference between logical processor and the physical processor? Processor is always a physical entity, right? Now what logical processor means here? Hello?
ALU in
Hmm?
Sir, because of hyper-threading, like the physical cores are split into one physical core is split into two, like two virtual cores. Like the computer will, the operating system will treat it as treat the single core as two cores, something like that.
Yes. So the point is, although I have got two physical CPUs, processors, so the hyper-threading technology, so that was actually implemented by Intel, and it was in the first time in February 2002, the Xeon servers, server processors, or in 2000, November 2002, Pentium 4 desktop processors. So they first
So you are not
even
audible,
if
sir.
hello, okay, so
No, it's
they
okay,
will
sir.
have, yes, so they will have mechanisms to use it as if there are two different CPUs. So instead of a physical CPU, it will act as two different CPUs, and when you assign processes or threads, you will have two threads or two processes which you can schedule and execute, right? So we are more interested in the logical number of logical processors. So in this case, as you can see, there are two physical CPUs, but there are four logical processors. That means each physical CPU is behaves like two logical processors, and that is what hyperthreading, the term hyperthreading means. So and in fact, once it is there, so that means in my machine I can run how many threads, how many executable units simultaneously,
4.
Four.
because after all, it doesn't matter how many physical, but how many physical you have, how many logical you have got, that is important, right? But definitely these four logical processors, the performance may not be exactly equivalent to that of having four physical processors, that we must know. But again, I mean, it is more or less, it is better than having just two processors. Okay, that is also obvious. So if I in the Linux environment, if I write the command ls cpu, so it will give this snapshot, and there also you'll find that the CPUs is 4. So CPUs is 4 means these are logical CPUs, and this is the core means uh, so it is actually 2, uh, and okay, these are the other details. And you have got, see, the RAM is 8 GB, and here also the RAM, you can estimate the RAM size and all this. So now that means in my machine I can take the advantage of creating multiple threads or even multiple processes. That is possible, right? So here, if I come to the thread implementation, so POSIX 1, so this standard specification, the threads are not better standardized but also available in most. So from this POSIX standard onwards, it has got the thread implementations, and which is also available in almost all the Linux distributions. But however, in the 1996, the Linux threads was first, it came, the concept of threads were first implemented, and it was by a person, I cannot recall the name, you can Google it, or you can check the wiki page of Linux threads, where it will be there. But because it's the first time that the idea of multi-threading or the threads, lightweight processes came, it has got several limitations, discrepancies, and performance issues. And the most important issue is like how many user level threads should map to kernel level threads, or whether this implementation will be a kernel level implementation or not. So these are the issues that need to be resolved and implemented. Okay, and in 2002, the native POSIX thread library, the NPTL was implemented, which actually it was in the line of Linux threads, but it has got those limitations to overcome. And there was a paper that was published in 2005, the native POSIX thread library for Linux. Okay, you can, if you want, you can go through this paper also. So we can assume that around 2002, that is 2002 or 4, the implementation of threads were there, and it was following some POSIX standards. And so this is
Sir, you are not audible.
So you are not audible, sir.
hello.
Yes, sir, now audible.
Hello. Yes. Yes, there are. I'm sorry, there are certain interruptions whenever the call comes. The connection drops because the LAN is still having a problem in my residence. So hopefully it will be fixed by tomorrow. So meanwhile, the multi-core processors were came, and as I mentioned that the hyper threading and even having multiple physical CPUs also, the systems were there. So as the standards were available, the hardware also is in abundance, so that you can exploit the existence of threads. Okay, so pthreads is a user level implementation, as you can see. So we have talked about Linux threads, we have talked about NPTL thread library. Now this pthreads is basically a user level interface specification. It's not an implementation. Okay, so pthread library, it provides an interface. So it is something like if NPTL defines a thread level system call, so this pthread library creates a wrapper which uh, which gives us a function interface through which you can call the thread library, I mean thread system calls. Okay, so pthread is basically a wrapper system, a wrapper function library which defines the specification, the interface. And as you can see that if this pthread library, if you use a pthread library, so this has got a specific interface for creating threads, specific interface for exiting the threads, for joining the threads or synchronizing threads and all this. Now if you think of having some machines, say Linux, some maybe say BSD Unix and all this, so they will all follow this implementation details. So using NPTL, so they will basically have some system calls. So these wrapper functions will basically wrap these system calls, and the user, as a user, if you write a high level application using this pthread library, so you can execute it, compile it and execute it here, any other machines which supports pthread interface. Okay, so writing something using pthread library makes it easily portable in different types of Unix or different versions of Linux and all this. And it actually uses NPTL say thread implementation. So that is how it works. And in Linux, pthreads is implemented using lightweight process. So this is a term that we will come across. This we call it as a lightweight process because we found that why it is called lightweight. And from kernel version 2.6 onwards, this implementation of NPTL is available. Okay. And what it says that NPTL is also is a one-to-one thread library. That means if you so in the kernel, if you create a thread, so that is visible in the, if you create a thread, that will be visible in the user space also. So kernel level thread, a thread that you created in the kernel will be visible in the user space. Okay, and the pthread in Unix implemented with NPTEL can take the advantage of multi-core CPUs. And the last point to note is this NPTEL uses the clone system call to implement each user thread as a lightweight process. So that is the important point to note. Okay. So what we found is NPTEL is available from mid 2000. pthread is an interface that will use NPTEL, and NPTEL, while creating threads, it will use the clone system call to actually create threads which are lightweight processes compared to creating a new process, entirely new process. Is this part clear till this point? Hello?
Sir, kernel
Yes.
level. Sir,
Yes.
kernel level thread means basically this thread is start means implemented by the kernel, or is it?
Kernel level thread means this is visible and schedulable by the kernel scheduler. This is maintained, scheduled by the kernel. Okay, so the kernel knows the existence of the thread, it keeps track, it schedules, it maintains, everything is done in the kernel space. Is that part clear?
Yes, but sir, every process which is running is scheduled by the OS. No?
Every process?
Every process which is running or is in the ready queue, they are all scheduled by the OS. So
Yes. So I'll come to it. I mean, once I show the examples, I think it will be clear. So in true sense, in Linux, if you create a process, that means that process will be created with a single thread of its own. So one process means one kernel thread, you can say. And that is visible in the user space also. I mean, maybe you better you hold on. I mean, till we discuss the next few slides, and if you still have the doubt, we can talk on it. So the first thing is the implementation of thread, the creation of a lightweight process, as we call it as LWP, uh, which is one major task of the NPTEL library or NPTEL implementation. It is achieved by the use of clone system call. So let us see what this clone is. The clone. So how we have created processes till now?
By fork system
Using
call.
fork, only fork. So what we know, if I create a process using fork, so the new process or the child process, what kind of overlap, what kind of commonality it will have with respect to the parent?
the code segment and
See, first of all, the child process will have its own copy of. I mean, first of all, these two are independent. So if you call for, so if this is the parent process, if this is child process, so first of all, the child will have everything same as that of the parent, like every entity. So if it has got 5-6 entities, like the files, the virtual memory and all this, the child will also have its own independent entities, but initially they will be copied, and once they start execution, parent and child will continue in their own way. So that is one extreme. Now I say that I will have some other function call through which, if this is a process, so I'll be creating not a heavyweight one. So I'll be creating these entities, or maybe I'll be creating this blue entity, which will have some of this, right? So maybe this much. Or I would like to create another entity which will be having this much. Okay. Or I'll be creating something which will be having this much. So the point to note is, like, I would like to have more flexibility in creating new schedulable entities, where I would like to have the choice to say that which things will be exclusive to these new entities and which things may be shared with the parent. Are you getting my point?
Yes, sir.
First thing is, in case of this one, you have no choice. So the child, once you create a child using for, then the child says that, so the mechanism says that you should have your everything of your own. You cannot share anything with the parent, because you are completely a new entity, right? But now you can say that, although I am creating a new entity out of this parent, I have the I have the flexibility, the power to say that how much I should have of my own, or what features I should have of my own independent, and what features I may share or I will share with the parent. Are you getting the point?
Yes,
So
sir.
it is either this option A or this option B or this option C, and in fact there are many other options. Okay, so you can use the options in such a way that you end up with this also. This is also possible, right? So this is more flexible. It's more fine tuned in terms of the choice that you opt, right? So and that is done, and this is basically done by use of clone system call. As it is done by fork, this is done by clone, and these are two different calls of clones. There can be many other possible ways. Now, what is the common feature? How many? If you look into that, how many arguments the clone system call accepts?
Sir, 3, 4, 4.
No, it's three, right? You see, this is one, this is one. Oh, okay, yeah, this is one, and the last one is, I mean, more or less ignored. So this is four, and here also one. This is two, this is three, and this is four. Got it? And in most of the cases, the last one is zero or null. I mean, we can right now ignore. So mainly there are three arguments, right? And what is the first one? Can you try to decode what is the implication of the first one? See, first of all, when we created child from the parent using fork, then so it is a different process, right? So any process should have some executable unit, some executable statements. So what the child executes in case of fork? What the
So,
child processes? Hmm?
so starts execution just
Yes. So
after
the
the.
thing is, so the thing is, the child process, uh, in case of fork, the execution continues in the child from the point where the fork is called, right? So basically the same code segment is copied here, the same code segment is copied here, and you basically start from that point where the fork returns, right? Everybody agrees?
Yes, sir.
Yes,
But in
sir.
case of clone, you don't do that. You rather you write a small function, right? And that function you pass here, and you can see ampersand, that means the pointer to that function, sorry, the pointer to that function you basically pass here. Okay, so this is what the child function, or do something, or whatever, f1. So the code that this new entity, these blue ones, whatever it is, that need to execute, and that will be separate entity, like they are scheduled separately and executed separately. So what they will execute, you have to put it in that function itself. That is one thing, and you have to pass the address of the function, and whenever you execute some different function, what you need, whenever a function is called,
The
what you need,
parameters.
the local variables need to be stored in the stack segment, right? And during the execution of the function, local variables keeps changing and all this, right? So you need a stack. So this is important, and because you are using a separate execution, a separate executable function, or you want to have a separate, you want to act as a separate executable entity, you need to have your own stack, right? So here what you basically pass, as you can see here, character asterisk stack. So you have to pass the pointer to some space which will be used as the new entities stack. Okay, is that part clear?
So will you repeat this part?
Before you call clone, you have to make sure that you write a function which will be including the code, the content of the code that you expect that to be executed. Second is, you have to create a space which will be treated as a stack for that new cloned, that entity, or you can say it's a lightweight process. So for that lightweight process, you have to create a stack, space for a stack, and you have to pass on the base address of that stack. So this is so this base address is passed plus the size. So you basically specify the area which will be used for the uh, uh, as a stack while this function is getting executed. Is that clear?
So why a character pointer, sir?
Okay, that is the way the clone system call has been defined. Okay, so you can go through the man page and find out why it is. But from the top level, let us first understand that you have to pass the pointer to the space to an area where which will be used as a stack for this new lightweight process. Is that part clear?
Yes, sir.
But to know that why it is like this and all, you can go through the man page, man clone, and you can find the details. Okay. And what is the third argument? Third argument is the most important part where you have the tuning ability. Now you see in the first case, in the first case, you see it is passing clone VM. In the second case, here it is passing, you see, clone VM, clone thread, clone sig hand. Now each of these flags, they have got some implications, some meanings, and this is or means you basically choose all these three. In the first case, you choose only the clone VM, and the second case you choose all the three cases. Now what this clone VM means, you see, it is set. If it is set, the calling process and the child process. I mean, through the clone, you assume that you are trying to create a child process, lightweight process, whatever, run in the same virtual memory space. In particular, the memory write performed by a calling process or by the child process are visible to each other. That means if you make it clone VM, means what is the major change, major difference with respect to fork that you make here? In fork, will the same virtual memory of the parent be shared with the child?
No, sir.
No.
No, sir.
But here, if you make while you are creating clone, trying to create a new process, maybe a lightweight process or whatever you say, if you specify the flag clone VM, you indeed can do that, right? So this is a lightweightness that you incorporate here. So you say that okay, the parent's virtual memory will be used by the child process also. So it is not in true sense the child in an ideal scenario that we expect in a fork. So this is the deviation. So this is here and this is here. Okay, and then this makes certainly a lot of lightweight because you don't have to create the entire virtual. You don't have to create the again the page map tables and the segment map tables need not be done because they are all sharing the both of the entities, the parent and the new one that you are going to create will be sharing that, right? Is that part clear?
Sir, if we set it to 0, then it will be independent, just like a fork.
Yeah, if you don't mention it, that means they will have separate entities, like it will be something like for.
Okay.
If you mention it, that means you are not so you are allowing it to be shared, so the separate virtual memory space will not be created for this new one. Okay,
Okay, sir.
so now if I focus on clone thread, what is this? If it is set, then the child is placed in the same thread group as the calling process. So we'll see that what the difference is. It's better not to discuss about it. And then clone sig hand, it means the calling process and the child process share the same table of signal handlers. Can you see this? So while discussing about threads, what was the basic idea regarding the signals? What we decided that the thread should be such that the signal handlers will be shared across all the threads, but the masks can be different, right?
Yes, sir.
So if I set clone sig hand, so it will be creating child processes which will be similar to the notion of the threads that you understand, right? Hello.
Yes, sir.
And in fact, I have listed only 3 or 4, but you can go through this tutorial, this page. I have listed there are many other tutorials. So you will have many such, like there are 8 to 10 such flags, and each of the flags have interpretations, and you can mix and match and find out which option you actually want. So you are basically you are having a fine-tuned ability to specify that when I create a new process, so what way it should be different with respect to the parent. Will it be completely different as like for? Will it be partly different? In what respect? That you can specify. Is that part clear?
Yes, sir.
So now focus on this code. So this is how I just call clone. So can you see this part? So this is a call to clone, right? and it is do something. So what is do something? Do something is a function, right? This is a function, and what it does, child PID. So it will display the child PID, and it will do this. So child PID means the new process that gets created, lightweight process or whatever, its PID will be displayed here, right? Okay, and then this is character stack and all this. So what I did here, void stack. So I have allocated some space for the stack. What is the size of the stack is this one, and I have passed that value plus the stack. So this I have passed, and this is clone VM. So that means the new process that I'm going planning to create will be sharing the same virtual memory with respect to the parent. And if it is successful, then so if I display this one, who is going to display this? Get PID. So the parent process will display, because the child process will be executing only this portion, right? The child process will be executing only this portion and nothing else. So it is not loosely defined as in case of for. It was more precise, because you have everything that you want to execute by the child has been encapsulated within a function, and you are passing the address of the function here, and you are creating the stack space, and you are passing it, and this is the option that how you are going, what type of uh, child process you are going to create with respect to the parent. So once it is done, so once the creation is done, now the parent will be executing this. So this get PID is the parent's PID, the original process's PID, and this is the newly created process PID, and then they will sleep and they will free the stack and they'll go to the infinite loop. So if I execute this PS hyphen ELF, can you see the columns? Can you specifically see this column and see this column? What is the difference? Now these two we already know, we are aware of parent ID and parent. So now what is this LWP? So what is the LWP of this process? Hello? Are you getting me? Hello?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yeah, so first thing is how many processes are created after the execution is done. It's going on a for loop. So how many processes are created? One is the original parent process, that was 168 PID, right? Whose parent
Yes,
is
sir.
actually 8. Now that in turn created 169, right? 169 whose parent was 168. That is obvious. Now what about this LWP? What it stands for? What do you think?
So lightweight process.
So this is basically, I mean, somewhat related to the thread notion. So this process, it has got a lightweight process map. It has got a corresponding lightweight process, or you can say a process will be interpreted as a lightweight process in a general terms. And this 169, its lightweight process ID is 169. So here we have got how many processes? How many processes are created here?
So
How many user
total
process are?
There
How many
two,
user process? Hmm?
there two.
Two user process, right? So one is the original one 168, one is the 169. But here the basic idea is, although they appear to be distinct processes, what do they share in common? What do they share in common? Their virtual space, virtual memory.
yes.
Okay, now you see, so there is a new command that I'm introducing. I think many of you have used it maybe earlier.
So what is
Anybody of
the
you?
so
Huh.
what is the LWP attribute telling us? Like what is the significance of it?
As I
LWP.
mentioned, so any process, any process will have a LWP ID or lightweight. So it's basically a thread. You can say LWP stands for thread. In Linux, LWP is actually associated with the notion of thread. That means this process, if there is a single process 168, that means it has one thread. So what it means is something like this. So this is 168 and this is 169, and it has got a thread 168 and this has got a thread 169. So these are
Sir,
LW. LW.
sir, but for every process, it is printing the PID itself. Here, 169 is the only lightweight process we created.
169.
169
Yes, as
is
I
the
mentioned. So as I mentioned, 168 was the original parent process, and 169 is a new parent process. Is a new process, or you can say it's a child process. And so this is the process, this box, and within that process you have got a thread. So this 169 stands for the thread. So every process will have at least one thread of execution, at least one. So once I execute this part, so you can visualize this, the processes and the threads like this. This is what has been created. But again, I mean, this is, so they have got some kind of overlaps. So these two, they have got some kind of overlaps in their virtual memory. Is that part clear? Maybe I mean, if you still have doubts, you please hold on. Let me just continue to the 3-4 slides so that you can relate later on, because now we are introducing the idea of LWP, which is basically a thread. So that might have sometimes some queries, so just hold on for a while. So is there any of you who have used the command top command in Linux?
Yes, sir.
Yeah, what it does?
It shows the like all the processes and the memory usage and the CPU usage.
Yeah, so it is something like the task manager, right? So this is when you type task manager in Windows, it will you will see the different tasks running or the processes running. If you would like to kill one of them which is not, probably it has got hanged and all, you can do that. So it is something similar to that with some more details. So if you type here top, you can find out the details of top in this hyperlink. Now if you type at the top, you see there are total 8 tasks as it says. So I'm taking the same the same example. Why 8 tasks? As you can see here, this init 1, init 2. So init 1, 2, 3, 4, 5, 6, and then these two are the user level tasks. So total there are 8 tasks. Okay, and then how many of them are running? 3. Why 3 are running? Why it is only 3 running? Which are the 3? Which of the 3 are running? You see the top command itself is running, and what else is running? The parent process and the newly created process 169 and 168, right?
Yes, sir.
yes, sir.
So there are 3 running and 5 are sleeping. Which are the 5? Init, bash, and all these are sleeping. And what is this percentage CPU utilization? What is this? So the uh, CPUs are getting, so total CPU utilization is 50%. But how many CPUs are there? How many CPUs are there? How many processors are there?
So 4.
4.
4. So if I just, while the top is running, if I just press 1, you see, if I press 1, then I'll have these details of the CPUs. Can you see this difference? This one is now kind of zoomed in. So you have got CPU 0, CPU 1, CPU 2, CPU 3. So these are the logical processes within each physical process. So you can have the details of it. Now you can find that more or less they are uniform, but it's not exactly. So let's 7, this is 2 and 3, and this is 7 and 6. Are you getting the point?
Yes, sir.
So now
Yes,
you know
sir.
how many processes are there. There are 3 running processes: top, this, and this. So there are 3, and they are somehow getting you know getting allocated to 4 of the logical CPUs or 4 of the processors. Forget about logical, physical. 4 of the processors that the OS can identify and schedule, right? And you can see here that the memory. So memory in bytes is this one. So this is approximately 8 uh, 8 GB. Okay, so here, and as you can see here, the details is uh, the virtual memory that has been used exactly the same. Can you see this? Because they are basically sharing the virtual memory space.
Sir, actually your markings are appearing late on the screen, sir.
Which one?
Yes, sir. Now your in circle came actually virtual. We cannot.
Yeah, I understand. This is a serious problem in the connectivity. Maybe till tomorrow you have to tolerate. I can't help.
Okay, sir.
I'm getting things. It was through tethering. I'm getting the access. So now, is it clear up to this point?
Yes,
Yes,
sir.
sir.
Yes, sir.
Sir,
So
one
to
thing to
summarize,
ask. So one
yeah,
thing to ask. Sir, when we are calling malloc, sir, isn't it allocating space in the heap segment?
yes, it
So,
is definitely in the heap segment. Sure, it
sir,
is
but
definitely in the heap segment. But you know the entire virtual memory is shared. So if it is shared, there is no problem. So it can access it.
but sir, in the clone function, we are passing the pointer to means malloc will
Hmm.
basically return the pointer to the means address of the heap segment to which it has allocated the memory, and we are passing that in the clone function. So means
Which one?
so in the clone function, we are passing the stack pointer, right? That
Yes.
so but stack pointer points to a segment of the heap memory, no, because heap malloc is returning some part of memory which is allocated in the heap. So
Hmm.
be- but technically it should have specified a segment in the stack segment
No,
of
no.
the
Yeah, I got your point. The thing is, this is not the in true sense the stack segment. So this is not a completely new process. It's a lightweight process. So it is trying to make use of the space from the existing process itself, but still trying to enjoy the benefit of having its own stack. That is the point. So that is how clone has been implemented. So clone says that the parent process is already having all the resources that is required to run a individual process, right? Now you are trying to create a new process which is often treated as a lightweight process, but that process should enjoy the benefit of having its own stack. So you are trying to assign some portion of memory from the parent process to be used by the lightweight process as its own stack area. Hello.
yes, I got it.
So it is not actually allocating a complete stack, completely separate stack segment. It is not. So it is like you are having something. So as I mentioned, so you have got the CSE department which was running quite fine. Now the CSE, now suddenly tomorrow the administration says that why don't you open a BTech in data science? That's all, a new program. So that new program when it is created, so you are not going to. So that does not mean that you the depart as a department will get some additional space, but you need to have some classrooms for this for this new program, some maybe some dedicated classrooms. So you say that okay, I am allocating this particular room which was lying vacant or which is utilized for some other purpose for the lectures, for holding the lectures of the BTech data science. Got the point?
Yes,
Yes,
sir.
So you are trying to have some mechanism so that that new program is also enjoying some kind of benefits of uh, benefits of having its own identity. That's all.
okay,
Okay.
sir.
So now you see there's, so these are different type of calls. So I don't have too much time, so let me just continue. Within another 10 minutes we'll stop. So can you see the difference here now? This again a call to the clone in a different way. So it's the function name is now changed. I have just intentionally changed it to child function. So this is a child function, so whatever it does I'm not bothered about that. Now the same thing, like the stack, whatever I allocate the space, sorry, here I just pass it here. Now the basic change is here. Can you see this change? Hello.
Yes, sir.
Now I have opted for not only clone VM but clone thread and clone seek hand. Now clone
Sir, are you on a different slide? Because we can't, we are
Yes,
seeing the
we cannot.
previous slide only,
okay,
We are
just
seeing the
the
previous
top
slide.
command one.
then you have to
We are,
wait for a while.
yes, sir. Now it's
Yes, sir, now it is
Yeah.
there.
Now can you see this one?
Yes,
Yes,
sir.
sir.
At the bottom. So now you have got, instead of VM clone VM, we have got clone thread and clone secant. So I try to plug in all the three flags together and see the impact of it. Now the more importantly, the impact will be created because of clone thread. Now what is clone thread doing? Now can you look into the snapshots and figure out what change it has taken place? In the PS hyphen ELF, actually L stands for, so if I specify the L comma, the L option here, can you see the L option? If I specify the L option, only then the LWP IDs will be displayed, otherwise not. Can you hear me, or still there
Yes,
is a
yes,
delay?
Yes, sir. Yes,
yes,
sir.
sir.
We
So
can
Yes,
hear.
sir.
yes,
if you specify hyphen E and then L, that L actually specifies the LWP IDs. Otherwise, it will not be shown, and people are not interested also. Normal application designers, but if you are really dealing with threads and all the details, you may be interested and you will be looking about what is happening here inside. So, can you see the change here?
So both have the same PID.
Yes, but LWP ID
Yes, sir. It is different.
yes, sir.
now.
Different.
Now, with respect to the previous example, do you find any change here? In the previous example, it was, can you
So,
recall?
so LWP ID was same as PID.
Yes, so it was 168, 168, 169, 169. Now it says it is, now it is 187, the parent process ID. The new child process ID also was 180, 187. But what you have in the LWP ID, it has got 187 and 188. So what can be the best way to interpret this? What is the best way to interpret this? So this is a box. So this box ID is what? 187, right? And it has got two threads, that is LWPs. One is 187, one is 188. Did it appear in your screen?
Yes, sir.
Yes,
Yes,
yes.
sir.
Now can you see the difference? The difference of this box and the difference of this box. I'm not sure whether it's visible. Hello? This difference?
Yes, sir.
Yes, sir.
Mm-hmm.
So now you know that just like plugging in different flags and in different options, you can play around and you can try to find out what exactly I would like to create. So here it creates. So how you define it in words? In words, what do I say? What
Sir,
is
in
the
a
intention
single
here?
processor, multiple threads are created.
So the intention is to create uh, another lightweight process. You see, whenever the parent is running, the parent was running with a single thread. That means 187 was running with 187 as a LWP thread, right? But now I say that I would like to create another LWP thread within the same process ID, right?
Yes, sir.
So this is the true notion of thread. So in the thread, what we wanted, the process should be the same, but I would like to create multiple threads within the same process. So the idea is the process ID also should be the same. And to make sure, we have to, what we need is to use this option. So clone thread actually plays the trick. So in true sense, when you try to create a thread, you have to use in the clone this clone thread with clone VM, because anyway the virtual memory is also shared. So like that. So is the difference clear?
Sir, does it mean multiple threads are created in a single CPU?
Multiple threads are created in a single.
Single CPU.
No, CPU is a processor. Why? How come CPU comes here? So the OS creates. So now here, what it does? Earlier also, how many schedulable units are there? Earlier in the previous example, how many schedulable units were there?
So two.
In the, huh?
So for the
In the
previous
Use.
previous example, two.
two, sir.
In
Oh,
this
yes,
case, how
sir.
many schedulable units are there? Also 2.
Yes, sir.
How many processors you are there? You have, at least in my machine, 4.
4.
So in the previous case also two threads with 2 different process IDs were getting scheduled. Now in this case 2 threads with same process ID is getting scheduled in 4 processors. That's the case. So in true sense, the previous one was not that much lightweight, but this is in true sense lightweight. Even the process ID is also shared, right?
Yes.
Got the difference? So what is the unit of scheduling? Is it a process or a thread?
So for this example, it is thread.
After knowing this all,
The thread.
hello, hello.
Yes, sir. Now it's okay.
Sorry. So got the difference. So what is the basic unit of scheduling? After knowing all this, what we can say?
Thread.
It is a thread, right? So it's a threads are basically the basic unit of scheduling. Now a thread, so it may happen that one process is just having one thread, so it is becomes trivial. So you can say that so basic schedulable unit is a process like that. That is also possible. But now with this flexibility, you can have multiple threads nested with multiple threads created within a single process also. So after all, the unit of scheduling is thread, not just a process right now. But when it is trivial that one process is having one thread, you may say that okay, unit is basic schedulable unit is a process. But after knowing all this, in a Unix system, in a Linux system, basic schedulable unit is no longer a process; it is a thread, or to be specific, a lightweight process. Is that fine?
Yes, sir.
Yes, sir.
And can you focus on this particular column? What it says? What it says is that number of lightweight processes that is under this particular PID. In this PID, how many lightweight processes are there? 2. This is 2. Can you see this?
Yes.
But in the previous example, can you see how many lightweight processes are there? It is 1, because so this means how many those spirals within the box. That is what it means. What is a box here? Corresponding to each PID, there is a box you can think of. And within each box, how many spirals will be there corresponding to the NWPs? Is that fine?
Yes, sir.
And how? What are the IDs? The IDs are in the LWP column. Is that okay?
NLWP stands for number of lightweight processes.
NWP stands for number of lightweight processes. Yes, it's a number. Now, can you see in the top when I execute top? So in the PID, so does it specify the LWP information? No. So at least in this mode, if you don't specify any other additional options, it just specifies the PID. So what is the PID? PID is in this case, I mean, so I taken it. So it should have been. So you see 187. It is 187 only. So it is not having entry corresponding to each LWPs. That I have to check whether the LWP option can be shown. So the top command displays the details of the information corresponding to each process.
They were not audible, sir.
Hello?
Yes, sir.
But here you see how many entries are here in this case. In this case, how many entries are here? 169 and 168, because they are having distinct PIDs. Okay? Is that fine?
Yes, sir.
Hello?
Yes, sir.
Yes, sir.
So just to complete it, as you can see here, the uh, pthread function. So we know that this using this clone nptl, what it creates a thread, right? And this pthread create provides the interface. So so creating a thread becomes as easy as this. So I'll go into the details of it later on. But when you use a pthread, I mean a thread using pthread library, PROSIX library, uh, I'll go to the details later on. But if I execute it, can you see which one it resembles, the first example or the second example? Just looking into these values, can you find out, figure out?
Second example.
Second example. So, and in fact that is what we mean as threads. So threads means the process id remains same, and you create multiple executable instances of that within that same process, right? So it actually resembles with the second one. So you can say that you can assume that when I call pthread create, in turn what which version of clone it calls? So it calls clone system call to create threads with what kind of option? Hello, which option?
So will you repeat the question? Who couldn't hear that part?
My question is, when I called a thread creation function provided by the POSIX thread library. So POSIX thread library. So when we deal with threads, it is not only just creating threads. There are many other options, many other operations on threads. So for manipulating or creating threads, we have got a thread library called pthread library, which is a POSIX standard interface which provides. So
Yes.
using that thread, in that thread library, we have got these functions like pthread create, pthread exit, pthread join, and all this. Okay, so pthread create, if I execute, you will find that it is creating lightweight processes following the second example. So to get it done, my question is, internally what pthread create actually executes, which system call it actually executes?
Sir, maybe fork.
Maybe for
No, why fork? Will fork give you this option to have this the same 283,
no, sir.
the process?
No, sir.
If you call fork, it will be instantly creating a new process ID, right? But is it doing so? So pthread create in turn executes what? It cannot execute fork. It executes which function call?
Clone. So clone.
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 And what version of, I mean, what type of clone? What kind of flags it should use? It should
The
use.
second
It should use.
example.
Second example.
Yeah. So more of like the second example. I mean, we can have. I mean, the exact details we have to check. But then again, as you at least you can expect that this clone thread is enabled. The clone VM is enabled and all this, right? Seek clone, clone seek hand is enabled. So it is more like that. So internally, you can think of when we write pthread create, it actually calls clone with that particular uh, flags. Okay,
Okay.
so that is how. So let me stop it here, and I'll
Sir,
start. Yes.
sir, how to interpret this in terms of CPU allocation? Because the concept of threads is based on the multiple processor.
Yes, as I mentioned. So once it is done, in the second example, once it is done, how many executable units are there? Say there are two user executable units. One is the top command. So three are the executable units. How many processors you have got? Three. So the scheduler, the OS knows that. The OS scheduler will know that, okay, I have got 3 units to schedule, and there are 4 units, 4 processors to be assigned, right?
Yes.
So there is no problem. So each one will be assigned to one of them, right? That's all. But if you have got more than that, like you have got 4 only, but you are trying to execute 20 threads, then lies the problem. So can it be so will it balance the load across and all that? So that we'll see in the next class. If you have created 20 lightweight processes, and I'm trying to run it in my machine, which is supporting 4 processors, logical processors, So how much load you expect in each processor?
Like
Say
5.
five of them.
How much load you expect in each processor? Each processor will be, I mean, 10% loaded, because uh, it will not sit idle, right?
Yes, sir.
But
Yes.
how much CPU share each lightweight process will enjoy? How much CPU share? Let us assume that you have 20 processes, 20 LWPs, and 4 processors. So that means 5 is allocated in each, right? So 5 is allocated in each. That means each LWP will enjoy what fraction of a logical CPU, logical processor? 1/5, right?
So what 20%?
Yeah, one
Sir, but
fifth, 20%.
there might be a limit, like how many threads it can execute
No, as
simultaneously.
such, there is, I mean, there may be limits, but right now we are not bothered about that. Definitely, there is always the system will have some hard-coded limits which can be exceeded. Okay, but right now, so we will talk about it in the next class, that if I create 20 such LWPs, how the CPU utilization is, and how the, so all these details we'll talk about, and we'll talk more about the pthread library, because once we know the internal details, we better focus on the system the actual thread library functions, so that we can develop applications using. But we know that in the back end what is actually happening, right? Hello.
Yes, sir.